In section 3.3, we're going to discuss a very important class of functions called uniformly continuous functions. And we'll find that every uniformly continuous function is continuous, but every continuous function is not uniformly continuous. Well, let's take a look at the definition of continuity at a point. Recall that the function f with domain capital D into the real numbers is continuous at a point x naught if for every epsilon greater than 0 there exists a delta greater than 0 such that the following is true. X in the domain and really close to x naught, specifically within a distance of delta of x naught, implies that the difference in the function values is less than epsilon. F of x minus f of x naught in absolute values is less than epsilon. And you may remember that we could put an upside down a in here. This means for all x for which this is true, this would be true. And f is continuous if it is continuous at every point in its domain. So I need to add one slightly different thing here at the very beginning. Notice that this should be identical to this. Now I have to say, for every x naught in the domain, and for every epsilon greater than 0, there exists a delta greater than 0, such that x in the domain and close to delta, close within delta of x naught, close to x naught, implies that f of x minus f of x naught is less than epsilon. So that's the definition of continuous, just continuous at every single point in the domain. Now, remember when we prove something is continuous, we just say let epsilon greater than 0 be given. It's your job and my job to find the value of delta that will work in this definition. And that when we choose that value of delta, it depends upon both what the value of x naught is, where we're trying to prove it's continuous, and the value of epsilon. So our choice of delta depends upon both epsilon and the value of x naught. But if we find a function f where the choice of delta depends only on epsilon, and it does not matter which value of x naught we're looking at in the domain, then f is uniformly continuous. Now, that's an informal statement. It's an informal, I'm not even going to call it the definition. We'll define it right now. The function f is uniformly continuous. Notice I don't need to say at x naught in the domain, uniformly continuous, on its entire domain, or I'm going to say on E, which is a subset of its domain. So it might not be, it's possible that the function won't be uniformly continuous on its whole domain, but if you pick some subset of it, that it will be uniformly continuous on that subset, for example, E. If. All right, we need a for every epsilon greater than 0, there exists a delta greater than 0 such that if we take x and y in the domain, and x and y are just dummy variables. If you wanted to call them x1 and x2, you could do that as well. But for every pair of numbers in the domain xy that are close to each other, the distance between x and y, or difference, absolute value of the difference, is less than delta, then what do we have? We're going to have f of x minus f of y less than epsilon in absolute values. Say f of x minus f of y less than delta. Less than epsilon. So you can see that this definition kind of includes the definition of continuity at a point. All you would need to do is say, call y x naught all the way along here. And you would be proving that it's continuous at that point. The thing is, we don't have to choose a different delta if we move x naught along in the domain. The same value of delta will work for everything. And this definition has a little similarity to a Cauchy sequence. Remember, when you have a convergent sequence, we prove, when we prove it's convergent, we prove that it converges to a particular point. But a Cauchy sequence, in that definition, it doesn't even include a limit in the definition. It simply says, for some capital N in the natural numbers, all of the indexes of that sequence that are greater than or equal to n are really close together. It's kind of similar to what we're saying here. All the way along the function, if any 2 points anywhere along the domain, if any 2 values on the domain are within delta of each other, the heights of the function, or the values of the function at those 2 points, differ by less than epsilon.